Good morning. I'm saying good morning because it is really early here at the school when I'm doing this video, but it's probably not good morning for you guys. Anyway, how are you guys doing today? We're going to go ahead and do, we have simple machines, and we're going to talk about the lever family. And this has lots of info in it, so we're going to learn it, and then the next day we're going to practice it, so don't panic if you don't feel like you understand it all just from the video. Alright, so let's talk about a wheel and axle first. This is the first one in the lever family we're going to talk about. A wheel and axle is a simple machine that consists of a wheel attached to a rod. A wheel and axle is used to lift or move objects. And wheel and axle rotate together. The force is applied to the wheel, and when the force is applied to the wheel, the axle, which is the rod, then turns. If force is applied to the axle, then the wheel will turn. The larger the radius of the wheel, the easier it is to use the wheel and axle to do work. So the radius of the wheel determines the mechanical advantage. The larger the radius, the better the mechanical advantage. Now, lever. A lever is a board or bar that sits on a fixed point called a fulcrum. The lever pivots or moves on the fulcrum. A lever makes it easier to lift and to lower objects. A lever can also change the direction of the force that you're wanting to apply. So here's an example of a lever. Here's our rigid arm or our board that moves on a fulcrum. The fulcrum is, I think I have it labeled right here. So if you press down and put a downward force on this side of the bar, then you're able to lift something on the other side of the bar. Alright, so the further the input force or the effort force is from the fulcrum, the greater the output force. So the greater the mechanical advantage. So the further the input force is away from the fulcrum, the more mechanical advantage, so it's easier for you. Okay, same amount of work can be done, but it's easier for you, and it'll allow you to lift something heavier than you originally started with. So if you'll look, the fulcrum on the left hand side is in between effort and load, and this one has less mechanical advantage than the one on the right because we moved the fulcrum away from the effort. The further the fulcrum is from the effort force, the more the mechanical advantage, the easier it is for you. If the input force is closer to the fulcrum, then the lever does not provide as much mechanical advantage. Now, classes of levers. Now, this is something that some students have a struggle with at first, so we're going to practice this in class. But there's just a hard, fast rule that I'm going to teach you that does help. There are 3 types of levers. With each type of lever, the location of the effort, the fulcrum, and the load changes. Okay? So in general, the types of levers are as follows. First class, fulcrum in the middle. First class starts with F, fulcrum starts with F, so the fulcrum is what's in the middle. Second class, the load is in the middle. Okay? Second class, the load is in the middle. Third class, effort is in the middle. The way I remember third class is E, looks like a backwards 3. That goes with third. So third class, effort in the middle. So first class lever, the fulcrum is between the effort and the load. It does not have to be exactly in the middle. Like, it doesn't have to be equal distance from them. It just has to be in between them. So an example, seesaw, pliers, scissors, and the output force is equal to or greater than the input force. So here's the fulcrum. Okay, this box represents the load. Whenever you see a box on a lever, that's representing the work you have to do, and then an arrow on the opposite side of the box is going to be where you're putting your effort. Now, the fulcrum can be moved closer to the load like we saw in a previous slide, and it still be a first class lever as long as it's in between the effort and the load. So here are some examples of first class levers. And so I want us to talk about how they, like how we actually determine if they're first class. So remember, your effort force is always what you apply, what the person is applying. So for the pliers, our effort is over here on the handles. That's where we put our hands. So that's where the effort force will be. The fulcrum is right here in the middle, and that's the turning point of the levers. And then where our work is done is down here at the left side of the pliers, right? Load represents work being done. So where I put my hands is the effort, the turning point is the fulcrum, and where the work is done is the load. So let's look at scissors. First class lever also, because fulcrum's in between effort and load. Our effort is placed on the handles of the scissors, and our work is done where we cut the paper or cut whatever we're working on, right? So these are first class levers. Second class lever. The load is in between the fulcrum and the effort. Some examples: wheelbarrow, can opener. The output force is always greater than the input force. So this is where, when you're using a second class lever, you're pulling up from the bottom of the bar to lift the load. And the load is in between the fulcrum and the effort force. Alright, so here's an example of a second class lever. So we place our hands on the handles of the wheelbarrow. That's where our effort goes. The work is done in the barrel, right? That's where we put the leaves or the dirt. So that's where our work is done. And then the fulcrum is down here where the wheel and axle is, because the fulcrum, that's the turning point, okay? And it's also where, when we lift the handles up, this is the part that stays on the ground, so it's the fulcrum. So the load is in between both of them, so it's a second class lever. Third class lever. The effort is between the fulcrum and the load. And remember, effort starts with an E, which is a backwards 3. That goes with third class. Examples of third class: fishing pole, tweezers, a broom. The output force is less than the input force. There is no mechanical advantage, but the distance to perform the work is smaller. So here we have our effort in between the load and the work we're being done and the fulcrum. Obviously, you can see that this is going to be a much more difficult. This looks like a hard lever to work, right? That's why there's no mechanical advantage, but they still can help us. So let's talk about that. So here are tweezers. Our effort goes right here where these rigid lines are. That's where we put our fingers. The work has been done down here on the left part. That's where the load is. And then the fulcrum is this part down here where both of them come together, and that's the turning point. So this is a third class lever. It still helps us get work done, right? And then broom. The fulcrum is up at the top of the broom. I'll show you this in class, but your hand that you put at the top of the broom helps create a fulcrum. And then your effort, you're pushing the broom in the middle, and then our work is being done down here at the end of the broom. So this is a third class lever. All right, our last simple machine that we're going to talk about in the lever family is a pulley. And this is a wheel with a groove around its outside edge. The groove is for a rope or belt that can move around the pulley. And the reason, I'll show you or talk to you in a second about that. Never mind. If you apply a downward force to one side of the rope, the pulley allows you to lift an object attached to the other side of the rope. A pulley makes work easier by changing the direction of the force or decreasing the force needed. So the reason this is in the lever family is because if you look at it, this is the fulcrum, and then the rope going around it is like the bar. It's just not a rigid bar like in a lever. So this is a movable bar, but that's why it's a part of the lever family. So we pull down on one side to be able to lift an object on the other side. Alright, so here are 3 examples of pulleys, and I want us to talk about the mechanical advantage of pulley. So pulleys, you can count the mechanical advantage by the number of support ropes. Now, the rope that you're pulling on over here on the left that says effort force, the rope you're pulling on does not count. So you can only count the supporting rope that's holding the load. So this is a mechanical advantage of 1. Now, the single movable pulley does not go by this rule because we have now changed the direction, so that gives us a mechanical advantage of 2, okay, because we've changed the direction of our force. And then, once you go from a single movable pulley and you start having multiple pulleys, the trick works again. You count the supporting ropes. We have one right here, and then we have another one in the middle. Don't count the one you hold. And the supporting ropes will tell you that this multiple pulley has a mechanical advantage of 2. So let's talk more about that. All right, a pulley system consists of 2 or more pulleys. So this is when we're going to be talking about multiple pulleys. With one pulley, the force required to lift the object is equal to the weight of the object. Let's show you what I'm talking about. So if you increase the amount of pulleys, you actually decrease the amount of force needed to lift the object for yourself. However, you must pull the rope proportionally more in order to lift the object the same distance. This is the same thing that we talked about in an earlier video. If I'm going to decrease my force, then I'm going to have to pull the rope a longer distance. Okay? So on this, I have to pull the rope 10 meters to lift the box 10 meters. Now, with 2 pulleys, if you noticed in that other, let's go back to the other picture. My force that I'm having to pull with is it's the same amount as the load, but changing the direction of the force, right, is helping me lift it up, but this has a very low mechanical advantage. So with 2 pulleys, the force required to lift an object is half the weight, because the weight of the object is distributed between 2 pulleys. So the person must pull the rope twice the distance, but they don't have to use as much force. Okay, so here our load is down here at the bottom. It's 100 newtons, that's its weight. But if you'll notice over here on the right hand side, we pull the rope with 50 newtons of force. So it's lessened the force for us because each pulley took part of the force, right? And it's decreased our force that we have to put in. But instead of lifting it 10 meters or pulling it 10 meters to lift it 10 meters, I have to pull it 20 meters to lift it 10 meters. So when my force decreases, the distance I have to use that force is going to increase, just like we talked about earlier. When you add a 3rd pulley, the force needed to lift the object is 1/4 the weight of the object because the weight is distributed 4 ways among the 3 pulleys, right? So we have our supporting rope taking part of it, one of our pulleys taking part of it, so each pulley takes another part, and our supporting fixed part takes a part of it, right? So now we only have to use 25 newtons of force, but we have to pull the rope 40 meters for it to lift. So it's easier for us, but we have to do it for longer, right? So if you'll notice, we start out with 100 newtons of force. So now I'm only having to use 1/4 of the force I started with, but then also my distance multiplied by 4, right? It increased by 4 times. So the person must, oh, here it goes. The person must pull the rope 4 times the distance to lift the object the same distance as with only 1 pulley, but it still makes it easier for us. So this is a higher mechanical advantage. The more pulleys you have, the higher the mechanical advantage. Okay, so that ended our video. So this is what I would like you to do. I would like you to draw or write the name of each 3 of the simple machines that we discussed, and I want you to put one thing you learned about each simple machine. I hope you have a great evening, and I'll see you in class.